again. This time the projector works. Yep. That is correct. So if you have the same number of permutations and each permutation is somewhere here, then it's fine. Yep. Yeah, that would make it easier for the generator because depending on how you keep track of the outcomes already acquired, sometimes printing it backwards is more uh, convenient. Yep.
You said on Monday that you'd show us in CoBlocks where to put in the
Yep, I forgot. Yep. Okay. So we'll do that first, making sure that the recorder is on. So we are streaming, so we're good now. So I'll show you how to do it in CoBlocks. So I do have CoBlocks here. It's an older version of CoBlocks. You guys can just download it, the latest version if you want to. But this part of the interface has not changed. So I'm going to go start a new project. So we go to File, New, and then start a new project. So when you start a new project, you have to select a console application. So don't select anything else. Your console application is the one that you need. And then click Go. Welcome to new console application wizard. Probably I don't need this, but I'll go through it just to see what it is. You have the option of selecting C versus C++. That part is up to you. Okay, if you guys want C, that's fine. If you want C++, that's fine too. So that's entirely up to you. And give it a title. I do not have any specific name that I want for this project unless it is described in the description. So I would just call it Omega, but it's up to you to describe how to decide the name of your project. And then I put it in. I'm just going to put it in a temp folder, which means it's going to be lost when I reset the computer. Okay, click next. GCC is fine. So we keep all of these defaults here, and then we click finish. So after we click finish, you will see under sources, let me go to the project view. This is the project view. We are under Omega already. So we want to create a new file. I thought it automatically creates a main. Huh? The new version does? Okay. Well, since this is not the new version, unfortunately, we have to start a new file. And we'll make it a C++ source file. And add the file to definitely debug and release. And the file name with full path. Oh, that may not be what I want, because I just want to create a file from here. Oh, it does. Okay. So it has a main.cpp automatically. So, that's how you start a project. So the next question is, how do we incorporate the arguments? I think that was the main point that I need to demonstrate. So the first thing we need to do is to put argc here and cons char star star argv over here. Okay, so that's the first step. Once we have these, then you can get to parse those things by going to project and under set programs arguments. Now you can specify the 3 numbers. So in this case, I'm specifying 2 and then the space and then the 4 and then a 0. And that's all you need. Okay, so you click OK, but I want to double check and make sure. So the one thing that I can quickly check and make sure is put a breakpoint in the program. And don't do this green button. The green button will start the execution of the program, but without going through the debugger. So the breakpoint that you have set is not going to be active if you use the green button. So when you're debugging your program, the best way to run the program is just to go to debug and then use the start continue inside the debug menu. Okay. So when the program runs, you will see that now we have a kind of yellowish triangle inside the stop sign. So that means the program has paused at that particular breakpoint. So at this point, under the debugger tab, there's a command line here. So you can print stuff if you want to. I think you can probably right click on variables too, but I'm just so much, okay, wrong place to type. click here, and then you can print argc, which should be 5, okay, 4, sorry, should be 4 because there are 3 and then plus the path of the executable itself. And then you can also print argv 0, which should be the path of the executable, like that, okay. You can also print the other argv members. argv1 should be of 2, which is a string, okay. And then the other two, should be here as well. I mean, I'm just making sure that we get all 3 parameters like that. So does that answer the question? Okay, excellent. So are there any other questions about how to set up the project in CodeBlocks? No question? Yep, go ahead.
So yes, Monday, at the top you have something like
Pound include a bunch of stuff.
like uint_8.
Right.
Something like that. Can we add that here too, or that only?
That part is up to you, okay? So, so this part is entirely up to you. You can pound include the same thing as on Monday, which is stdint.h, that's standard integer.h. And then the other one that I also pound included was stdlib.h, standard library.h. So each one is providing me something that is nice to have, but not 100% necessary, okay? So standard library is giving me ATOI, or ASCII to integer. So I can convert the string 2, 4, 0 to the actual value of 2, 4, and 0 and store that in an integer so I can pass it around.
I was actually talking about something else. You were saying that we could use like I believe it was, yeah.
Mm-hmm. I think that was this, right? 32 underscore t, and then I define my own, type called set.
So that's not only for C sharp, that we could use that in C++.
I was using plain C on Monday, so just about everything you can do in C, you can do in C++. I think there is like a very few occasion where it is in C but not in C++. But for all practical consideration, everything that I can do in C, you can do it in C++. Yep. The nice thing about C++ is most of you are probably familiar with how to use cout, as opposed to printf or some other non C++ way of outputting. Yep.
How can we get access to the to this 240, like to this argument,
Mm-hmm.
inside of the program? Aren't we gonna need them?
Well, exactly that. argv bracket 0 is the path, but when you refer to argv1, that's always the first number. argv2 is the second number, and argv3 is the last number. And I did promise on Monday that I'm not gonna. You will not need error checking, so I will always pass you an actual number for those 3, so you don't have to do error checking there. Yep.
How do we set the arguments?
Sorry.
How do we set them? Just so clear.
Reset.
Set the arguments.
Set the arguments.
Yes. How do we set them? So that we know it works.
Are you referring to this portion under project and set programs argument? Is that?
How do we set the arguments
To see what works?
Okay.
Okay, so the program right now is working the way it's supposed to, because inside the program, at this particular breakpoint, I was able to, okay, let me close this first. So at this particular breakpoint, I was able to access the 3 arguments that I passed. So we know the strings are there.
How did you pass them?
Huh?
How did you pass the arguments?
Exactly what I just did earlier. This is how I pass the argument. You go to project and then go to set programs arguments, and that's how I pass the 2, 4, and the 0. Is that okay? Yep.
So the 2, 4, and 0 is considered their strings?
It's considered 3 strings here.
Yeah, 3 strings.
Yep. Mm-hmm. So 2 is 1 string, 4 is 1 string, and then 0 is 1 string. And they are in argv 1, 2, and 3. Yep.
What is the difference of regular input and this way of input?
This way of inputting means that you do not need standard input
Oh,
because it is actually on the command
oh,
that starts the execution of the program. Yep.
Just to verify, so for this project, we need to create functions and then in the main section, just write like a little program that's gonna throw out that.
Right. So the objective of the program is really to output all the permutations based on the number of trials, the number of choices for the first trial, and based on whether it is with or without replacement. So that's the bottom line. Now, can I do everything in main? Well, the answer is actually yes. Okay, you don't actually need subroutines or recursion to do this, but the non-recursive version of this program is, I think, significantly more difficult compared to the recursive version. So I do recommend the use of a recursive function to do it. But there's no particular restriction as to what features in C and C++ you can and cannot use. The only restriction is it has to be your code. It has to be your code in C or C++ to get it done. But as long as it is your code and you say, well, I want to do everything inside main, I don't need any other subroutine, that's doable. Okay, would I suggest it? Probably not, but it's possible. Okay, if you want to break it up, and make it really clean, each subroutine only has like 4 to 6 lines, but you end up with like 20 functions or something like that. Well, that's the other way to do it. So how you organize your program is entirely up to you. I do not, put any restrictions on that one.
when you just submit your CPP file, just one single file?
You need to submit all the files. So what you need to do is to zip up the entire folder and then send the zip file to me. Yep. So if you're doing code blocks, just zip up the whole folder, including the project file, and then submit the zip file. If you're doing it in just regular C file, then you just zip up the .c or .cpp and then .h files, and possibly the make file if you know how to use a make file, and zip it all up and then turn that in. Yep.
Single file C file, single file C source is fine.
Say again.
Just a single C source file is fine.
If you can do it in a single .c file, yes, then you just need one single file. Correct. Okay. Any other questions? Any questions about the mechanism itself, the whole thing about recursion and what you need to do inside recursion, that sort of thing? No questions? Okay. All right. Well, if you do think of any questions, let me know during the lecture. So I'm going to leave code blocks up just in case there are any additional questions. And then we go back to the notes. I haven't started yet a browser, so let me go ahead and start one. Oh, the program, by the way, has now paused. So that means if you want the program to continue execution, you go to debug and then you just click start/continue, because the continue will continue execution if it is already paused. Okay. And now the program is done. And the reason why I know it is done is because it says right here, inferior one, process 1669 exited normally. So this is basically what you want to look for to signify that the program is done. It has exited already. If your program gets into an infinite loop, how do you break the infinite loop? Let me show you what I mean by that. So let's say you have an infinite loop of some kind. So you have, say, let's say while one. I'm not sure whether this will work or not, because the compiler may be smart enough to complain about it and not even compile. So we'll see. So we'll see whether I can get myself into an infinite loop like this. So we go start, continue, and it is now okay. It didn't get into the infinite loop. Because I know because it's right here. Well, maybe it's an infinite loop because I don't see that message here. So now you can go to debug, and you can say stop debugger. Actually, it's not at a point. Okay, I take it back. The program is not running anymore because the moment you see the yellow triangle, it means the program has paused at that particular point. So this program did not get into an infinite loop. So I have to do something a little bit smarter because I think the compiler understands this is not a good thing to have. So we'll how about this? Okay. So I'm doing this time, but without the semicolon. What does that mean in C without that semicolon? What is the difference between the one with a semicolon, which is what I had, and this one that is without a semicolon?
Fuzzy order, the command ends. So it's gonna run
It's gonna run hello.
forever
Yep.
until it hits one, but it's never gonna hit one because we don't even have a counter.
Right. But with a semicolon right here, it means I have an empty statement. So it's trying to do an empty statement forever. And the compiler was probably smart enough to go like, no, this is not something that's good, okay? But right now, we don't have that semicolon, which means, okay, the construct of while is saying, okay, in this case, I'm forever doing whatever is next, whatever the statement is next. So in this case, the next statement is the C out. So this program should spill out hello world forever, okay? So we'll see whether that's the case or not. Okay, so we'll go ahead and reset the debugger. So you can always stop the debugger so they can start from scratch, start from the beginning again. So now we start that, and okay, I have a breakpoint here, so I'm going to remove the breakpoint first. But it's going to get into that infinite loop for sure. So you can see in the background, it's actually printing hello world like crazy. So now how do I stop the program? Because it has an infinite loop. You go into the debugger, and then you type break debugger. Okay? Stop debugger, not only will it actually stop the entire process, it kills the process, which means there's no way for you to find out where you are stuck in. So you want to use break debugger, which basically just means, okay, stop running and tell me where you are. And let's see, it's not at a place where it can really display where it is, but that's okay because we know that command that can show us where we are. It's called BT. Do you guys still remember BT? With any type of recursive subroutine, BT is going to be really useful. Okay, so BT shows me all the frames that I'm in. In other words, right now, when I click that button, pause or break debugger, it is inside a subroutine called __ write no cancel, which is called from _IO _new _file _write, which is called from new _do _write, and so on and so forth. Did I write those subroutines? No, these are all coming from the standard library or whatever is linked with the program. So what I really do care is all the way down here. This one here, look at the last frame. The last frame said blah, 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 blah. They're all triggered on line 12 of main.cpp. So it's this line. So I now know, where in my code is causing this infinite loop. Okay, so that's a really important debugging technique, because if your program, you click something, your program gets into an infinite loop. The first thing is you don't want to control C, because control C actually stops the execution and kills the process. Then you have no clue where you were when you were in the infinite loop. So you want to pause the execution of the program and then use BT to find out which part of your code is inside the infinite loop. Is that okay? All right. Okay. So any other questions? Okay, here is a question. Okay, so I'm now at a place the program has stopped execution, but I want to go back and find out what is argv2 at this point from main. Okay, so if I just say print argv bracket 2 and the enter key, it says it's not in context. Well, it really is not in context, because as far as the frames are concerned, argv is an argument of frame number 8. Okay, the current context by default is frame number 1. I don't even have the source code of frame number 0. Sorry, it should be 0. So there's no way it can know how to print argv2. So if I want to print argv2, then we need to use the other command that we talked about on Monday, which is frame. Okay, it's just frame, and then you tell the debugger which frame you want to go to. We want to go to frame 8, okay? Because frame 8 is where my code is, okay? So we type frame 8, then it confirms, okay? It confirms that we are in main .cpp line 12, okay? So now in the right context, in the right frame, I can ask the question again. What is argv2? Now it knows what argv2 is. So when you're debugging recursive subroutines that may potentially enter an infinite loop, all of these techniques will come in handy. Okay? The good thing is it's all getting recorded, because I know most people could not retain like maybe 20% of what I just said. And it's reasonable. I understand, all of this stuff, you will remember it once you have done it like twice or 3 times. Okay? But if I'm just talking about it, like that. Okay? But what you need to understand right now is what it is for. Okay? Not exactly the details, but what exactly is it for? In what situation is this important? So are we good so far? Yep. All right. Cool. All right. So I'm going to leave this one here for now, and we'll go back to the notes. Yep, go ahead and restore. And I'm also hoping that at least some of you remember why the omega generator can be useful. Do you guys remember what example did I use the other day to show that there are cases where you want to generate all possible permutations? Which board game did I use as an example? Mastermind, exactly. Yep. So it's just a good thing to kind of keep that in mind, because that's something that can be, maybe at some point in your career, that will be useful. Okay, so let's go back to discrete probability, and we are pretty much done with this entire module. So the last one is just observed empirical probabilities, because we are done with talking about the binomial theorem and also the binomial distribution. Do you guys have a recollection of this stuff? Yes? Okay. So all of this stuff here, if you want to kind of have a mental picture or to visualize all of this stuff here, the one thing that is the most visual is Pascal's triangle. Okay? So Pascal's triangle relates directly to 2 things. It relates to Pascal's identity. It also relates to the binomial theorem. So you have to kind of associate those things and connect those items. Okay? So what we'll do today is to say, well, let's say you go to a casino, okay? And I don't even know whether they have games, or whether you can gamble on coin flips or not. Does anyone know? Okay. Does it surprise you that I do not go to any casinos? Okay. So let's just say that they do. Okay. So they have games, or they have gambling involving coin flipping, and you can place your bet on how many heads out of X number of coin flips. Is that okay? All right. So let's just say that you're betting on experiments involving 5 coin flips. So let me write it down here. So we go to accessories, go to mouse pad, and we say that, okay, so each experiment has 5 trials with replacement, and each trial has 2 outcomes, and the set of outcomes is simply head versus tail. Okay, so that pretty much summarizes that particular gambling scenario. Okay, 5 flips of a coin, each each trial, has two possible outcomes, either head or tail. It is with replacement because, once you have heads up, the next one can also be heads up, which means, you're not removing an outcome from the set, from your subsequent trials. Okay, so now the question is, under nominal conditions, okay, when the coin is fair, okay, it is not loaded, what is the probability of 3 heads and 2 tails? That's my first question. Okay, so I'm going to write it here. What is the probability? What is the probability of 3 heads, 2 tails? And the ordering is not important. Okay, I don't really care, which flip ends up with a head and which flip ends up with a tail. I'm just adding them up. Okay, 3, 2. What do you think? How do we calculate this? So remember the concept of an event versus the concept of all possible outcomes. Okay, so what event are we talking about? So the event is the set of all permutations ending up with 3 heads and 2 tails. What about omega? In other words, what is the set of all possible outcomes? It will just be, if I need to list it out, it's going to be all heads, head, 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 tail, tail, head, 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 tail, head, 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 tail, head, head, and so on. Head, tail, head, 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 tail, head, 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 and so on. Okay? And the probability is really the cardinality of the event that I'm interested in divided by the cardinality of omega. That gives me the probability. Okay? In order to find out what the probability is, I need to know the cardinality of the event as well as the cardinality of omega. So let's start with omega. Omega is the easy one. Okay? So I'm flipping a coin 5 times. Yep, go ahead. It will be 2 to the power of 5. Yep, 2 raised to the power, the 5th power of 2. Okay? Because, I'm flipping the coin 5 times. The first flip can end up with a 0 or head or a tail. The second flip, independent of the first one, can also be a head or the tail, and so on. So I end up with, 2 to the power of 5 possible permutations of outcomes. So omega, if you look at just the cardinality of omega, is 2 to the power of 5, which is 32. So now the next question is, what about events? Okay, how many ways can I choose 3 heads out of 5 coin tosses? Whoops, didn't I just say the answer? Yep. 5 choose 3, yep. It would also be equal to 5 choose 2. Now that part, why 5 choose 2 and 5 choose 3 are the same has to do with the definition of choosing. Okay, but you're correct. So the number of events is, there are many ways to write it. Okay, in the spreadsheet it's called combin. So it's 5 choose 2. Okay, this is what you need to enter in the spreadsheet. But you can also, in mathematics, you can also say this is just 5 choose 2. That means exactly the same thing. But what exactly is 5 choose 2? I mean, what is the actual number that we are dealing with? It's 5 factorial divided by, so I'm putting a big parenthesis here because there are two components in the denominator. So the first one is 2 factorial, and then the second one is 5 minus 2 factorial, which is 3 factorial. But this is also why 5 choose 2 and 5 choose 3 are the same, because you're just flipping these two around. Do you see what I mean? Okay, so 5 choose 2 and 5 choose 3 are always exactly the same, but graphically it makes sense too, because if you think about Pascal's triangle and you pick up the row that corresponds to x plus y to the power of 5, the middle two numbers are the same. Okay, so it makes sense from multiple perspectives. Okay, So now we look at this number and go like, what is that? 5 factorial is 5 times 4 times 3 times 1, which is 120. 2 factorial is just 2 itself. And then 5 minus 2 is 3. 3 factorial is 3 times 2 times 1, which is 6. So the answer is 10. Is that okay? Okay, I can see a whole lot of skepticism here, okay? But that's fine. So what we'll do is we're going to go take a look at Pascal's triangle, okay? Because that's one really graphical and visual way to double check these things. So we'll do a Pascal's triangle, okay? There's one. Now with Pascal's triangle, you can actually use a very interesting equation, which is the value of a particular value is always the sum of the parents or whatever number is above it, the two numbers above it. You go like, but that doesn't seem to work with this one. That is correct. That one has to be the seed of the entire thing. So what you can do is to kind of imagine you don't really have just one here, okay? So I'm going to give you a quick, interesting way of coming up with Pascal's triangle. Think of that one is in a sea of zeros on the first row, okay? So on the second row, what you do is this number is the sum of the two numbers on top of it, which is a 0, right? 0 plus 0 is a 0. 0 plus 0 is a 0. 0 plus 0 is a 0, blah, 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 blah. 0 plus 1 is a 1. 1 plus 0 is a 1. And then we end up with all zeros again after this. Is that okay? On the next row, okay, these are all pretty boring. See, this one, this position has 0 on top of it and also 1 on top of it. 0 plus 1 is a 1. 1 plus 1 is a 2. 1 plus 0 is 1 again. And then this one ends up with 0 and 0 on top of it. So they're all zeros from here on. Is that okay? And then the next row, kind of the same deal. This is a 1. This is a 3, 3, 1. And then zeros after that. Oops. Okay, 1, 4, 6, 4, 1, and then a bunch of zeros again. So you can see how, this is another way of constructing Pascal's triangle, is basically just to say every number is the sum of the two numbers on top of it. But you have to imagine that this is an infinite sea of zeros with a single 1 on the first row. After that, this works, okay? We have one more row to go to get to the one that we want, okay? Okay, so here's a 1, and this is a 5, a 10. Oops, okay, it doesn't line up anymore. Okay, we'll use A here. Hexadecimal, huh? There we go. All right, so what is this? 5 choose 2. 5 choose 3. What is this? 5 choose 5. 5 choose 0. 5 choose 1. 5 choose 2. 5 choose 3. 5 choose 4. And 5 choose 5. In other words, I'm trying to give you as many ways of representing the same thing as possible, because that will, hopefully, it will help build up more pathways in your mind to connect the concepts. Is that okay? And this is really graphical too, which is kind of nice. You can kind of imagine this is the wake pattern of a boat going up. We'll call it Pascal's boat. So are we good so far? All right. So what is the probability? Because we have to go back to the original problem, okay? Enough digression. So in the original problem, the probability is now 10 divided by 32, which you can simplify to 5 divided by 16. So what is that? That's a little bit more than a quarter, okay? Is that okay? So this means, depending on the payback ratio of this gamble, okay? Because with gambling, you're basically putting down X amount of money and say that, okay, I bet that this experiment will end up with 3 heads and 2 tails, right? But your chances of winning is your chances of getting the correct guess is only 5 divided by 16. So that means, the casino, in order to entice you to place your bet, they have to say, if you're right, we are going to give you X amount of money. So at a certain point, it's going to break even. Okay, neither you nor the casino is making money. Okay, what is the payback in order to make it worthwhile? Hmm? Say that one more time. Drinks. Okay. So the way you calculate the payback to break even is to think of the extreme cases. Okay. So if this number is 0, in other words, there's 0 chance that you can end up with that particular pattern, then it doesn't matter what the payback is. You're always going to lose money because what you're guessing on, what you're betting on, can never happen. Does that make any sense? So that is kind of like, well, it's kind of like infinity. Okay, think of it as infinity. What if what you're betting on is always going to happen? It's 1.0, 100% of the chance what you're betting on is going to happen. Well, in that case, if you place a bet of $1 to break even, the casino just pay you back that $1. So the payback has a ratio of just 1. Okay, to guarantee that you do not lose any money. Is that okay? So basically, it is the reciprocal of this number. Okay, if the probability of guessing correctly is 5 divided by 16, then the payback ratio has to be 16 divided by 5 in order for you not to lose money and the casino is not losing money either. Because of the few chances that you actually guess it correctly, which is about a quarter time, they will pay back about 4 times. So if you place a bet of $1, they pay you back $4. Okay? But the chances of that happening is only about a quarter of the times. So you're not losing any money, but you're not gaining anything either. So that's the quote-unquote fair payback ratio. And this is how casinos or sports betting and all kinds of other gambling. That's how they work. Okay, it all has to do with the chances of your bet, you're placing the correct bet versus the payback ratio. That determines the profitability of a joint that's involved in gambling. Are we good so far? All right. So now you look at this number, you go like, okay, so in the long run, okay, if I observe like 20 bazillion of these experiments, okay, and take the average, I should come up with this number, okay? 5 times out of 16, we will observe, 3 heads and 2 tails, okay? So let's say you went in and actually do the observation, and it turns out to be a number that's larger or smaller than this, okay, over a lot of observations. The more observations you have done and still confirm that the number does not even come close to 5 divided by 16, the more confidence you have that the coin is loaded. Is that making any sense? Okay, so that's one of the theories behind observation or statistics is if the more observation you're making and it's still skewed and not going to the theoretical number, then the more confidence you have that the coin is loaded in this case. It also applies to dice, okay, throwing dice, which means you have 6 possible outcomes instead of 2 if you're using a 6-face dice. I know there are dice with more faces as well, but it's just a matter of having more possible outcomes. So do we have any questions about this part here? No questions? All right. So now that you have taken this class, you're not going to go to the casino. You're not going to bet on anything. You're not going to buy the lotto ticket. Okay? So what good is this stuff if we're not betting, we're not gambling, we're not buying lotto? Well, I bet you some of you will still be computer engineers, network engineers, and so on and so forth. So you're still dealing with gambling, and this time you do not have any control over the odds. Is that making any sense? Okay, so let me give you an idea here. You transmit a 1. It can be received as a 1, which is good. Okay, let's say that's most of the time. But because of communication error, a 1 transmitted can also be received as a 0, right? And the same thing happens when you're transmitting a 0. The 0 transmitted can be received correctly as a 0, but occasionally it can also be received incorrectly as a 1 because someone decides to turn on the microwave oven. Okay? Or a bird flies in between the two, the transmitter and the receiver, and get cooked in the same because of that. You guys know how microwave got discovered for cooking purposes, right? No?
It was the sonar, remember? It melted the guy's chocolate in his pocket.
It's a microwave transmitter. Yep. So it melted something, or somebody felt warm around it, and then they found out, hey, microwave can be used to heat up liquid, okay, that contains water. It actually heats up oil as well, okay, but that's how they found it out. That's ended up as our microwave ovens. Okay, but anyway, we are concerned about transmission errors here. Okay, so now the question is, if over a whole lot of observations, I say, well, this happens 95% of the time, this happens 5% of the time, this happens, let's say, 97% of the time, and this happens 3% of the time. In other words, through empirical testing, we gather the statistics, okay? If you transmit a 1, there's a 95% chance that it is received correctly. If you transmit a 0, for some reason it's not symmetric, and there's a 97% chance that it is received correctly, only a 3% chance that it is not received correctly, okay? Now, for our first example, let's assume they're the same, because if they're different, the analysis is going to be a little bit more difficult. So we assume they're the same first, okay? I take this back, and they're the same. Okay, there we go. So now the question is, this is for only 1 bit, okay? So now the question is, if I transmit a 1 kilobit packet, what are the chances that the entire packet is transmitted correctly? Do you see what I mean? Okay, so let me write it down, okay? So the question is, what are the chances that a 1024-bit packet is received correctly? What do you think? What do you think? How do you compute that chance? Well, for bit 0 to be received correctly, there's a 97% chance. For bit 1 to be received correctly, there's a 97% chance, and so on. So that means we have to multiply 97% chance 1,024 times. Okay? So that number, this probability turns out to be 0.97, okay, 0.97 to the power of 1,024. What do you think that number would look like? Doesn't sound too bad, but this is compounding. Okay, so this is the quote unquote magical part of compounding stuff. Okay, because the first one is 97%, the second one is about 94 point something percent, then the next one is going to be 91 point something percent. So it decreases rather quickly at the beginning, but when it gets down to close to 0, then it doesn't decrease nearly as fast anymore. It is exponential. Okay, so this number turns out to be pretty bleak. Okay, let's figure out how bleak it is. And let's see, I'm going to use a spreadsheet. Let's see, where's my apps? There we go. Okay, go to cisp440. And I'll put it into shared, okay? But since I don't really have any particular name for this spreadsheet, we'll just name it after today's date, just like the other ones. There are many documents here that are only named after a particular date. Okay, we'll call it 2018-1024. And we'll go ahead and do some calculations here. Um, before we do that, we'll say the probability of being correct is 0.97. Whoops. 0.97. And so that means being incorrect is going to be 1 minus the correct probability. And then we'll say packet size in number of bits, which is 1024 this time. So now we want to compute the probability of a packet transmitted correctly. Transmitted correctly. There we go. So we use the power function. So that is the correct probability to the power of the number of bits in the packet. And it says it's 0 because it's very close to 0. Okay, so how close to 0 are we talking about? Huh? Okay, so we can go to number and go to scientific notation. Yep, there you go. So if that packet, if you're playing League of Legends, okay, and this is one of those UDP packets that you have to send to the Riot server, and the transmission error rate is only 3%, forget it. You're not going to play that game. Hmm? What? More like what? You can't even report anything because you cannot transmit anything to Riot's server. You might as well write that letter by hand and then start walking to Riot's headquarters, and you might actually deliver your message before your computer can transmit correctly to the headquarters of Riot. Yep.
Out of sheer curiosity, do you know like what transition error rates are for
Oh, it has to be extremely low.
I can explore Google, but I just want to.
Yeah, so you can play with these numbers, right? You can say, yeah, what if it's 99%, which means the only error rate is only 1%, right? Yeah, it's still pretty bleak. because if I talk about the chances of a packet transmitted correctly, and we're talking about some random TCP/IP protocol for business use, nobody pays attention. When we talk about game protocols, everybody wakes up and go like, what? How do I reduce my lag time again? Okay, so 99% is not quite good enough. Okay, so what about 99.9%? That sounds pretty good. It's 0.359. Okay, the chances of a packet as one whole thing, as one 1024-bit packet transmitted correctly, is still less than 1/2 of the chance. And that's with one individual bit having a success rate of 99.9%. What if you add another 9 to this? So 99.99% of the chance it is actually transmitted correctly. Now things start to look a little bit better because now we are saying there's a 90% chance that your packet will go through correctly, which is still pretty bad because if you think about it, there's a 10% chance that it's not going to go through correctly, or at least one bit is incorrect in that packet. Is that okay? So does that kind of give you an idea of why probability is really useful in real life? Okay. So of course, most of the time, we want to do the calculation backwards, which is specifying, okay, what is the tolerable transmission error rate on a packet level? Then you go back to figure out what is the per bit transmission error rate that is actually doable, that's actually livable. Okay. So that's kind of the thing that we're dealing with in real life. So gambling, transmission errors, sort of all kinds of stuff like that relates to probability distribution. Are there any questions at this point about probabilities, um, combinations, permutations? Yep. How does a computer generate random numbers? Um, well, we wish computers actually have truly random numbers, but they don't. Okay, so that means because there's nothing inside the computer that is truly random, that is unpredictable. Everything actually has a certain pattern to it. Okay, so when what we call entropy refers to the it kind of equates to randomness. So when entropy is actually important, what those programs want to do is to ask the end user to move the mouse pointer, to type on the keyboard and do all kinds of stuff, because the user interaction is a lot more random in nature compared to mechanisms that are inside the computer. So you might say, but what if I draw circles around using the mouse pointer? Isn't that really kind of predictable and not really that random? Or if I type on the keyboard, the timing between key presses, that's pretty regular too. I mean, it's not random at all. Trust me, there's actually a lot of randomness to it. It all depends on how microscopic you're looking at, in terms of the time interval. Okay, so let's say you're a very good typer, okay, or typist, okay, and you can type in a very predictable way. If you're typing THIS, it's always like that. Okay, so let's just say that your your variance between key presses. Okay, so I'm going to go back to here. So let's say the variance between key presses is only between 25 milliseconds and 26 milliseconds. Okay, no one can actually type with that type of consistency, but let's just say, right? Okay, so your consistency is between 25 to 26 milliseconds. How fast is your computer clock running again? It's in gigahertz, right? So that means the resolution of your computer's timing mechanism is far better than this. Okay, that 1 single millisecond in between. Okay, so we are looking at a 1 millisecond in between. 1 millisecond is 1,000 microseconds, which is 1 million. 1, 2, 3, 4, 5, 6. What goes after micro? Nanoseconds. Okay. Oh, okay. So what are the chances that you can have regularity within the nanosecond range of timing? You cannot. There's simply not a way for your muscles, your tendons, all the physical stuff, the keyboard itself, temperature variances, to have any type of predictability within this time frame. Within milliseconds, yeah. Within tens of milliseconds, absolutely. I mean, that's definitely a pattern to it. But when you look at things at a very small level like this, anything that we do, okay, anything that is human-based, with our physical input, is going to be pretty random. So that is one potential source of randomness. Now, what if you say, but I really need true randomness without human interaction? How do I get that kind of randomness? Yep. Quantum mechanics, yes, or the decay of a radioactive, material. When that thing comes out, okay, it can be a beta, it can be an alpha particle or whatnot, but the timing between those things coming out is random. Okay, so you have to resort to physics and radioactive, material when you want, that level of randomness. Who would need that kind of randomness? Oh, okay, let me back up a little bit. Why do we need randomness? Crypto, exactly. And why is that again? What happens when things are not random enough? Why is it less secure?
Predictable.
Because it's predictable, exactly. So if once things becomes predictable, then security goes down to the toilet. Okay. Now you might ask, what kind of stuff needs that kind of unpredictability? encryption of your browser's cookie, for instance. Okay, why is that important? What if the session cookie that Wells Fargo Bank or some other financial institution that want your computer to store is simply a sequential number? Okay, 1, 2, 3, 4, 5, 6, and so on. Well, you can always kind of guess, okay, within a certain time frame, somebody is going to have a session cookie of a particular number because it's a sequential number. Is that okay? So you can now tell your hacked browser and say, oh, we'll just go ahead and store this particular cookie, plant this cookie into the browser. So when the financial institution, computer communicates with your browser or your client replies back and go like, yeah, I got this cookie of this number, okay? Well, the other side, the server is going to say, oh, I can see your cookie with this number, which is a very simple sequential number, matches what I have passed out 2 minutes ago to some other computer, okay? And then the server is now going to say, yep, I know you. You are Mr. Blah, 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 and here's your account summary. What do you want to do with your account? Would you like to transfer? In other words, if you can predict, okay, the encrypted cookie, if you can predict the encrypted cookie value for session management purposes, then you can potentially hijack sessions. Okay. Now, somebody is going to be so smart about networking and go like, yeah, but the network address, the IP address is not going to match and you cannot hijack anything. Fine. Think of this scenario. Your roommate is doing a banking session, okay, inside the router, okay? You go like, oh, Jimmy is doing some banking with Wells Fargo. Let me run back to my computer. Okay, because you're now guessing based on the time frame. You can kind of guess what number, if it's a sequential number, Jimmy's browser is going to be using. Okay, so let's say by the time you get to your computer and open the session, your session sequential number is 2016. Okay, but that's like only moments after Jimmy has opened his session. So you can kind of go backwards and say, I'm guessing Jimmy's session cookie is going to be a number between maybe 1950 and 2015, okay? So you have a range. So what do? Well, you keep hitting the server with every single number within that range until it works. So at some point, you will be hijacking Jimmy's session. So now you know how much money Jimmy owns or owes. But it's okay. Either way, as long as transfer is possible, you transfer some funds into your Swiss account. But IP address is not going to help now. Why not? Because you're inside a local area network. So to the outside world, to the bank server, they all come from the same IP address. So there's no way for the server to differentiate between Jimmy's computer versus your computer. Okay, so I'm glad that you point that out. Okay, we do not want predictability, and why? Because we don't want people to be able to do that sort of thing. Is that making any sense? Okay, does this enable you to become a hacker now? Nah, not even close. If I can think of this, the financial institutions have already plugged all of those security holes years, if not decades ago. But the idea is the same, okay? Okay, so the next thing is, okay, I'm digressing a little bit, but I think it's necessary, okay? These are the things that actually is important when you get out there to get jobs, okay? So, okay, if a sequential number is not good enough, okay, we're not using sequential number. Now what do? Oh, I heard about this thing called MD5 hash. Okay, MD5 hash is a very simple hash function where you give it something that's small and it'll give you a somewhat randomized bit pattern. Okay, but MD5 hash is not a one-way function, not anymore. In other words, people can look at an MD5 hash and go backwards and say, oh, I know this pattern is going to generate that MD5 hash, which means it is now possible, if a cookie is only based on MD5 hash, it is now also possible for a hacker to observe a few times, to observe a sequence of these MD5 hashes and go back in time and go back and figure out um, how, what is the actual sequential number behind the hash value, which means, once again, it's hackable. Okay? Yep.
One random question. So if you have 80 fixed bit hash,
Mm-hmm.
would that hash necessarily have to contain collisions if you're hashing data that's bigger than that? If you have a 26-bit hash,
Yep.
you're putting in 43-bit numbers or 52-bit numbers.
It's bound to have collisions.
It has to, yeah.
Yep. It has to collide. Yep. Because there's no way not to have collision. Oh, but that's a very good thing to bring up. Because if a hash function is a function, what is the property of that function now? Is it injective? You can give it two things to hash, but they hash to the same value. It is no longer injective. So what if something is not injective? Okay, let me go back a little bit. How do you think, okay, go ahead. You cannot inverse it to one single value because there are multiple values that can map to a single, the same hash value. That is correct. Okay, so I'm digressing a little bit more, but I think this is actually a useful discussion. How do you think passwords are stored? Okay, it's okay. This is just my laptop computer. So if you go to okay, so I'm not going to show that because I'm not so concerned about you guys, but I'm concerned about the other YouTubers. Okay, so when you store a password in a system, okay, the password itself is not stored in plain text. In other words, if my password is 123, okay, it's not going to create an entry anywhere that says 123. What the computer is going to store is a hash value of 123. Now, it's MD5 hash is not secure, but now SHA-2 is still considered relatively safe for like normal user accounts. Okay, so it's a hash value, which means 123 as a string is now generating a big, huge, gigantic, bit pattern. If you want to know what it's going to look like, it's pretty easy. You just go to a website, go to Google, and say, Google SHA-2, and see if, great. First thing that pops up is, Google just cracked one of the building blocks of web encryption. Test, or, okay, let's say test. Let's see. To check transition from the SHA to the, I want to compute it, so let's see. Calculator? Yep, there we go. All right. So we can enter the text and it will give me the hash of that particular value. So let's say my password is just 123, and then I press. How do I get the hash here? Doesn't have a button. Okay, so hash value is like this. So 123 hashes to this kind of gigantic hexadecimal representation. So that is the one being stored on the computer. So the next time I try to log in, on the keyboard, I type 123 as my password. So what the computer is doing is it is turning what I type into a hash value, and then it compares the hashed version of what I type with what is stored on the computer. So it's only comparing and storing hashed values and not the original string. Is that okay? So now the question is, if I were a hacker and I have access to this number, the hashed value, what do I need to do? Well, I cannot just enter this hash value as password. That's not going to work. So what I need to do now is to say, let's go backwards and see if I can find a string that can give me this particular hash value, which 123 is one of those strings. But is 123 the only string that can give me this particular hash value? The answer is no. there can be different strings that can give me the same hash value. And as long as I can find a string that gives me the same hash value, I can sign into that system. Is that okay? So MD5 is problematic because the hashed string is too short. So that means people with enough computation power and enough hard drive space can now pre-compute a whole table of possible hashed values. So if you know what a hash value is, they can now reverse and go back and say, oh, we know at least this string can generate that particular hash value. So once you have the hashed value, you can now break the you can break the password. You can reverse and find a password that works. Okay. Yep.
Is it the same way? Like, there are many like, if you try to download some kind of virus program, there are many like keygens and stuff like this. They work the same way pretty much. So people get like some kind of one password, they convert to hash, and then basically they get like a whole bunch of other passwords. They work for the same purpose.
I do not know exactly.
Yeah.
But I know the concept of a keygen. So if people want to get an unlicensed version of Windows to install, they have to key in like the 20-digit code, right?
No,
Yeah.
I'm not talking about Windows. I'm just talking about general.
I do not know, but the rainbow table is the reverse hash table. So basically, it stores all the possible hashed values, and you can reverse back to a string that can generate that particular hashed value. So this is well known already, and people already know this, and that's why MD5 hash is no longer considered even close to secure. So really kind of interesting stuff. I digressed a little bit, but still useful stuff. All right, so getting back to the stuff that we are supposed to talk about. So probability is mostly done. So the next topic, I think I can let you guys choose. There are a few things we can continue to talk about. We can talk about graph theory. We can also talk about predicate calculus. So let me describe a little bit, so that we can have a little vote maybe next time. Graph theory is about finding shortest paths, okay? Or what we focus on is how to find the shortest path. Okay, so you represent a map, and then you measure the distance between the nodes or between the intersections, so to speak. Okay, and you have a whole big, huge database of that information. So now the question is, what is the quickest way to go from this intersection over here all the way to that intersection over there? And we have a lot of interconnections in between. So that problem of finding the shortest path is going to be discussed in the graph theory part of this class. And we're going to use the A-star algorithm as well as the Dijkstra's algorithm, okay, to solve that problem. So that's one. If we go the other route, we'll be talking about predicate calculus. Predicate calculus is kind of like an extension of propositional logic, but it's a lot more fun, okay? Okay, so I'm going to show you a slide so that you know why I say it is a lot of fun, okay? So let's open it. And it's because you can do it interactively using Prolog. So all this stuff here is kind of, okay, so this is starting to be kind of interesting and fun. Okay. Look at this. Doesn't that look fun to you already? Doesn't it sound like something that Yoda would say? He's a Jedi Luke Skywalker. Okay, that sounds pretty Yoda-ish. Yoda-ish, okay? So this is what we call a predicate, okay? A predicate is kind of like a proposition, except it's parameterized, okay? So in other words, Luke Skywalker is a parameter, and then is a Jedi is kind of like a proposition, kind of like a statement, and it is true, okay? So it's given to be true. This is in the iota. And the really fun part is we can specify quote-unquote rules. Okay, what does that mean? Okay, so this symbol here is only if. Okay, it is not if, it is the reverse. It's only if. So we are basically saying X is a proper Jedi only if X is a Jedi, comma is and X owns Y, and Y is a lightsaber. So in the end, all it really is saying is, in order for someone to be a proper Jedi, that person has to be, quote unquote, a Jedi first, owns something, and that something is a lightsaber. Okay? How cool is that, right? But if this is not enough for you and say, well, but that doesn't really define what a Jedi is, then we can, let me see if I actually have that one. I think I do. Negation, disagree with. Okay, so here, this is it. I think I haven't really finished typing the entire thing. Okay, so if I want to define whether a particular person is Sith tolerant, okay, how would I define that? Okay, so I would first have to find, okay, find me a Sith, Y, okay? And now I have to say X has to be not disagreeing with Y. If I can find a Sith such that X does not disagree with that Sith, then X is called Sith tolerant. Okay? So it has a lot of the stuff that we talked about with propositional logic, except this time, you get to play with it because all of this is actually proper Prolog code. So you can actually put it into a Prolog program. You can put in a whole bunch of, you can put in, quote unquote, a database. Okay, so you can predefine, who is a Jedi, who owns which lightsaber, blah, 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 blah. Okay, and now you can ask questions. You can say, is Yoda Sith tolerant? Okay, and go through the whole database and try to find an example of Yoda not disagreeing with a particular Sith. Okay, if Yoda is known not to disagree with a particular Sith, then Yoda is Sith tolerant. Okay. You can also kind of imagine you have a family tree. Okay, so you can enter a family tree into Prolog. Okay, who is whom's father, who is whom's mother, and so on. So all you need to enter are parental relationship. Okay, because that automatically establishes sibling relationships. Okay, so you enter that whole thing, and then you can ask, show me all ancestors of Tommy, and the program can actually go through the entire database and find all the objects that can meet the rule of being the ancestor of Tommy. Or you can ask a specific question, okay? You can say, is John an ancestor of Tommy? Then the system would go through all the logic and reply with either yes or no. Okay, is there an ancestry tree or path between those two individuals? If so, it would answer yes. If not, it would say no. So it's a really kind of interesting AI-ish kind of programming language. It was one of the main programming languages in AI back in the 80s. Okay, it was used by the Japanese as well as the Europeans, when they were doing a lot of symbolic AI stuff back in those days. Okay, so that's your pick. Okay, we don't have to choose now. Okay, I can prepare notes on Monday for both of these topics. So graph theory, kind of practical, finding the shortest path and stuff like that. Predicate logic, has to do with AI, how to do reasoning when we have parameterization and stuff like that. So I will let you guys choose, okay? So on Monday, I will ask the question again, and then you guys can tell me which way to proceed. And choose wisely.